The best garbage collector is a myth. If you're trying to build your own garbage collector or trying to pick a garbage collector for your specific use case, there are 7 parameters that would objectively help you decide which one to go for. These parameters define a garbage collector and it determines its performance on your specific workload. In the previous video, we talked about why programming languages need an automatic garbage collection, primarily because engineers are unreliable. And in this one, we talk about the 7 key metrics and characteristics of a garbage collector that can help us compare and judge which one is better than the other for a specific workload. This is not theoretical, but something that all senior engineers spend their time to get the best performance out of their systems. But before we move forward, I want to talk to you about a code-based course on system design that I have been running since March 2021. Right? If you are looking to learn system design from the first principles, this course is for you. Yeah. Because this is a cohort-based course, it will not just be me rambling a semi-optimized solution thinking it's the most amazing solution out there. Instead, it will be a collaborative environment where every single person who is part of the cohort can pitch in his or her ideas and we will evolve our system around that. Right? Every single problem statement comes with a brainstorming session where we all together brainstorm and evolve our system. That's way everyone understands the kind of trade-offs we made while making that decision. Instead of just saying, hey, we'll use a particular queue, we'll have the justification why we use only that queue, why we use that particular database, why SQL, why not NoSQL, right? How are we leveraging throughput? How are we ensuring that our system scales? That's the highlight of this course. This course is taken by more than 500 engineers to date, spanning 9 countries and 7 cohorts, right? People from all top companies have taken this course and the outline is very intriguing. It's very exciting. So we start with week 1 we start with the core foundation of the course where we design online offline indicator, then we try to design our own medium, then we go into database where we go in depth of database locking and see few very amazing examples of database locking in action and how do we ensure that our system scales through that. Then the third week is all about going distributed where we design our load balancer. I'll walk you through the actual code of a toy load balancer and understand how TCP connections are managed and how simple it is to build load balancer. Then week 4 is all about social networks. Week 5 is all about building your own storage engines. Like we'll build that intuition on if you were to ever design your storage engine, how would you do that, right? Then week 6 is about building high throughput systems. 7 is about building IR systems, basically information retrieval systems and ad hoc designs where we design our own message brokers like SQS where we design distributed task scheduler. And we conclude the course with week 8 where we talk about the super clever algorithms that has powered or that has made those systems possible. Right? I have also attached a video verbatim as is from my first cohort where we designed and scaled Instagram notifications. I will highly encourage you to check this video out. Right? And now back to the video. So the 7 key metrics of a garbage collector are pause time, safety, language specific optimizations, completeness, throughput, space overhead, and scalability. There will not be one GC that is doing great at all of them. There would be some GCs who are great at throughput, great at pause time, great at safety, but they would be suffering from scalability. They would have very high space overhead, and they might not do a lot of language specific optimization. Right? So when you're doing this comparative analysis between GC, you try to plot this 2-dimensional web plot across all of the GCs on all the parameters that you can think of and see which one fits your needs, right? And you should be picking a GC that fits your needs, fits your workload in order to get the best performance out of it, right? Again, best garbage collector is a myth, right? There is always one which is better than other in some particular use case. And if that particular characteristic or that particular use case is something you need, you have to go for that particular GC. And obviously, when something is good at something, it is also bad at a few. So you get the best, but you also have to suffer the worst for those extra parameters. Right? So there was a study done in 2000s around garbage collectors, and what folks found out that each one of the garbage collector is superior than the others in at least one use case by 15%. This clearly indicates that, hey, there is no one garbage collector that is best across all, but every garbage collector will be better than all other in at least one use case by 15%. So, which means that if that is that one use case that you direly need, you would have to go for that garbage collector. Right? And most garbage collectors, now to get the performance, how do you get performance out of your garbage collector? Most garbage collectors, they give you a lot of knobs. When I say knobs, like these are all sort of tunable parameters, which would help you tune the performance of your garbage collector for the load that you are handling. Some examples, like these are Java specific examples, but any language you pick, every language or every garbage collector that you pick in every language, there are a lot of parameters that you can tune. Go through the documentation to understand it. Just a few things that I would want to point out is like XX, use serial GC, use parallel GC, max GC pause millis, like this would define what's the maximum time your GC should be pausing, GC time ratio, mean heap free ratio and all. So there are 50 more parameters that you can tune depending on the GC that you have chosen. But it's when you are picking a GC, when you are tuning the GC to the best performance, you need to know, hey, these are all the parameters that I can tune. This is my workload. Run the test and see how it is behaving. And to be really honest, after a certain scale, after a certain scale and after a certain stage of your career, you will be spending more time tuning these parameters than coding. True story. And it always happens. To get that best performance out of it, because after a certain time, the GC pauses will hurt the performance of your system. And which is where you would be spending a lot of time tuning the performance out of your system to get that extra ounce of throughput. Right? Now what we'll do is we'll go through the 7 characteristics and understand each one of them and the kind of impact it has. First one, safety. What safety says is that a collector must never reclaim the storage of live objects. Basically, it simply means that it should not be deleting an object which is already in use. So if I have 2 object pointers, object 1 and object 2, and they both point to the same object in memory, right? And now if this object is deleted, these 2 pointers become dangling pointers. So what we want is 0 dangling pointers, right? So if 2 objects are referring to a particular place in memory, which means it's live, so your automatic garbage collection cannot delete this or cannot reclaim this space. Right. So this is something that garbage collector should be doing. So this says that you say that a garbage collector is safe when it does not delete an object which is live. But like I said that on safety it might rank low or in safety it might rank high. What does this mean? This means that not all garbage collectors are 100% safe. There might be, there are some garbage collectors to do better on other parameters. It might also reclaim the space which is in use. Not that frequently, but it can do. Right. So safety, if that is one of your most important criteria, you have to go for it. Like it obviously has its own repercussions, but yeah, you have to bear the load. The second one is throughput. Obviously, everyone wants my time to spend on garbage collection should be as low as possible. No one wants to say my garbage collection can go for hours. Obviously, it does not, but no one says that. So everyone wants our program and garbage collection to execute in as little of a time as possible. That's a very, very shrewd requirement. Right? So what happens is if I would want to plot a very simple box plot on if this is the 100% of your time, how much time goes into program execution, how much time goes into garbage collection, you get a very nice skewed 99:1 or 90:10 ratio. 90:10 is massive, but 99:1 ratio. Right? So during that 1% of the time, hypothetically, your GC is running. When your GC is running, in most cases, it would be the stop the world GC, which means that when GC is running, your program cannot execute. So now, if your GC is slower, then your GC is taking longer time to execute, then your program is getting lesser time to execute, which affects the throughput of your business logic. For example, if you're running a payment service, having a lot of transactions, and if your GC kicks in, program execution is affected, your payment service is affected. Right? So you don't want your GC time to be very high because it would hog into your program execution time. You want to give the best performance to your user, but you still want to run GC. So that's a kind of a dilemma. So what GC typically does is most GCs, they have short burst of they have short cycles, they have cycles of short garbage collection and then a long one, right? So this short one, what GCs do is to ensure that your program gets enough cycles to execute. Your program is having a lot of throughput, or your main business logic is having a lot of CPU cycles to execute. Your GC would try to run a quick garbage collection in a very short time. Right? This would ensure that your program throughput is not affected. But then once a while, GC would run an expensive defragmentation that would go for a longer time. And then it would do it to, because of all the shorting that it ran, it was not able to fully clean up the stuff. So that is where this long one comes in, and it does this massive defragmentation or compaction, whatever you want to call, and it does it once a while. So you would always see short burst of GCs and then a long pause. A short burst of GCs, then a long pause. And that is how most GCs would operate, just to improve or just to make your overall throughput of your program or of your business logic as high as possible. The third one is completeness. So completeness implies that, hey, all the garbage that is there in my heap should be reclaimed. The keyword here is eventually. Right? So it implies that there should not be any object left in the memory that is a garbage, which is no one is pointing to that object, but it is still lying there. A repercussion or a side effect of this would be memory leaks. If you are not deleting all the objects that are not referenced ever in your system, then what it would lead to is memory leak, because now slowly and steadily all of these objects are just lying there on your memory, never cleaned up. So it would increase your memory usage and slowly, and this is a classical case of memory leak. So which is where what completeness says that, hey, a garbage collector is complete where you want to eventually delete all the garbage that is there, or you want to collect all the garbage that is there in the heap, right? So eventually, so it might again that one, instead of doing it in one cycle, you can do it eventually, but it has to be complete, right? So it may not happen in the first cycle, second cycle, fourth cycle, but maybe in the 10th cycle that objects gets reclaimed, right? But that needs to happen. There should not be any object that is deleted or that is not referenced, but it's still lying there, right? So eventually it needs to be cleaned up. The fourth one is pause time. This is the most important parameter out there, most important characteristic out there. Pause time is most or more often than not, when a garbage collector runs, it pauses the program execution. So this is called as stop the world GC. So this stop the world GC is when my GC is kicking in, it has to do a lot of computation, it has to do a lot of object movement here and there. So it would require your program execution to stop. So the threads that do that execution are called mutator threads. These threads are stopped and only garbage collection threads run, right? And when this happens, your business throughput or your program throughput is 0, which is why it's called stop the world. And this metric is one of the worst. Like basically, if this is high, it is directly impacting the throughput of your business logic, and everything would go for a toss, right? So that is where this is something that every senior engineer dreads. Oh my God, we are having a stop the world GC, like Elasticsearch, pick any infra component, pick any, like specifically Java service, you would see this more often, that there are so many stop the world GCs happening, in which you would have to see your systems fail, error rates going high, your program execution stopped, your transaction needs to be restarted, and so many things. So which is why, and it's like, why do we need stop the world GC? Why such exclusivity to GC? It's not that just because GC needs to run fast, you're giving full CPU to it. The main reason is, once a while, your GC would do defragmentation. It means that, let's say I have this as my memory layout. These are all the objects that are allocated. The red ones are the ones which are deleted, right? So once these objects are deleted, what needs to happen is that if I just delete these objects, the other objects would be lying there in memory, but they are not compacted, which means that if someone wants a very large object, it might not be able to fit in this available memory because memory allocation needs to be continuous. It needs to be continuous, right? Memory allocation needs to be continuous. So if it needs to be continuous and if it does not have that big of a memory chunk, that big of a continuous memory chunk available, then it will not be able to allocate object, right? Which is where once a while your garbage collection does a defragmentation or a compaction, in which once these objects are deleted, it would reshuffle the objects such that it would leave a large chunk of continuous memory available for allocation. Now, when the objects move, here object 1 and object 2 moved from this location to this location. Basically, these three objects were deleted. So, these object 1 and object 2 moved over here so that all of the objects are closely packed. And when this happens, you get a very nice large free chunk of space available over here. So, now what happens is when this object movement is happening, right, when these objects are being shuffled, your program execute, because when objects are being shuffled, it's the actual memory address being changed from one to other. And when that happens, what your program, like if at the same time your program is also executing, what would happen is your program will point to some other location which does not exist and all of those complications would kick in. That is where your GC says, hey, let's stop the world. Let me quickly move all the objects. Let me quickly do the defragmentation so that the way the objects are referenced in the memory, they still are correct, right? So maintain the correctness of the references that your objects point to. It needs to stop the world. And once the object movement is done, then the program execution resumes. And this is what causes the stop the world, or it basically causes the pause time of GC, right? So what garbage collector does is it tries its best to reduce the pause time to as low as possible. But when it tries to reduce the pause time, it has its own set of challenges, because the side effect of this is you might not have a large chunk of continuous memory available, your GC might not be complete and all. That is where it's just a combination of short cycles and long pauses that happen. So once a while you'll have a long pause, otherwise you'll have a short burst of cycles. Then you would run compaction once a while and you would not be complete, you would be eventually complete. So many things are affected by this, right? But you would always try to optimize your workload like such that your program does not impact very high. So you'll tune a lot of parameters to ensure that your GC pauses are at minimal. The fifth point is space overhead. GCs, obviously, when it needs to identify which objects to delete, which objects to not, it has to maintain a lot of auxiliary data structures to track which objects are being referenced, how are being referenced, which one to delete, why to delete, when to delete. So your GC itself has a space overhead, right? So when it has a massive space overhead, it would need memory for its allocation. And so it would put an extra pressure or extra load or extra consumption of your memory. So a good GC to again, space-time trade-off. If you have a large amount of space available to allocate, or if you're using a sophisticated data structure, you would find which objects to delete in a very short time. But if you have a very poor data structure, you will take a long time to do it. But that poor data structure might be efficient on space. So that is where again a trade-off to make. Hey, which auxiliary data structures is my GC using to perform that need? So what is the overall space overhead of my garbage collector? And to do that, again, there is no way but for you to test it on your dev environment, on your local environment, and see how much of a space overhead of the GC is there. Right? So that if it fits your needs, go for it. Otherwise, rethink your decision and go for another. Like if you have a very memory intensive application where you have very strong constraint on memory, you cannot bear that extra space cost. You can bear on time, but you cannot bear on cost. Some weird use case, right? So then you would want to go for a GC that is low on space overhead, right? Like few examples of data structures that GCs use, like bitmap tables. So bitmap tables they would use to check which object is already picked for cleanup, which object is not, which object is moved to other generation and whatnot. Something we'll look into future videos. And then graphs to maintain, hey, this object depends on this object, this depends on this object. So if I clean this object, I would have to clean the other two and whatnot, right? So extra data structures, GCs need those data structures to be able to find out whom to delete, why to delete, quickly able to find out and all of that. So space overhead, again, a critical metric to consider. The sixth one is language specific optimizations. So every language is different. Every language has a different set of features. So can a general GC algorithm take leverage or can leverage the language out there? No. Like if you go for a very basic GC algorithm, it is language agnostic, works across all languages, then it might not be best for a particular language. Because let's say there are some languages which are pure functional. There are some languages that only have heap allocation and does not allocate on stack. There are some objects that may have explicit deallocation, like where you have to call malloc and free and all. There are some languages that have only persistent data structures. Now, which means that if you know, or if your garbage collector knows that this is the language on which it is running, so it can run that extra optimizations, where it can exploit the features of the language, where features of the language as in how objects are allocated in memory, how are they mapped into memory, or what kind of access pattern do objects behave. Like if a language only has persistent data structures, then every time you make any modification, it will create a new copy of the data. So you can very easily run a quick deletion of the past references of the objects which are not in use. Then a way through which you know that if a particular language is store the allocated objects in a particular order in memory, you can leverage that. For example, there are a few GCs that run in constant time because of how objects are laid out in the memory manager. So the runtime of a memory, whenever the object is allocated, it's stored they are allocated in a particular way in the memory of the language. And if you know that this is how the objects will always be allocated, you can quickly find out, okay, hey, how to do my GC in constant time, because that's the way the objects are allocated in the memory. And depending on other ways of allocation, other ways how objects are created, objects are deleted, objects are referenced, you can make a lot of optimizations on a garbage collector. So which is where you will always find most garbage collectors out there, they are language specific garbage collectors, because they exploit how that language is built. They exploit how that language does object allocation and other part of it. Then the final point around this is scalability. The garbage collectors were being built from like last 20, 30, 35 years. The first set of garbage collectors are still around. The garbage collectors that were built back then were built for few MBs of RAM. Now we have few 100 GBs of RAM, like which is an insane amount of scale. So here, even with garbage collectors, scalability is extremely important, because a GC or a garbage collector written 30 years back might not be performant enough, like might be good for few MBs of cleanup, but not for few 100 GBs of cleanup, right? So a GC needs to leverage the modern hardware capabilities. Like the modern hardwares are parallel. If a GC is not leveraging multiple cores, then not a good choice then, right? So it needs to leverage the hardware better to get the best performance out of it. And that is where a GC needs to evolve. A classic example of that is because servers are growing, the RAM of a server was initially few MBs, now it is few 100 GBs, if not terabyte. Obviously terabytes RAMs are there, but still few hundreds of GBs at least. And hence, when a GC would kick in, cleaning up few MBs is very small task. Clearing a few 100 GBs, your GC would be running for a very long duration. And now let's say if your GC was a stop the world GC, like every time it runs, it stops the world. So going through that few 100 GBs of heap every time, and if it is every time stopping the world, then your program execution is suffering so much. Which is where your GC needs to know, or it needs to evolve itself such that even if the memory is high, it is still not always stopping the world for its garbage collection. Right? And it needs to do the memory management in the most efficient way possible, because there is a massive space to iterate and go through. Like just iterating few GBs of RAM of memory itself takes a long time to do so. Right? So which is where your GC can be very, like an old GC might be very inefficient for the modern workload, which is something that you have to always keep in mind. Right? So there are now, to handle large amount of servers and to handle this large load, there are some GCs that are pause free, because when they operate on few hundred GBs of RAM, they cannot do always stop the world. So some GCs have evolved and new features have been added to it, which are pause free, which would never lead to any pause time. But obviously it has impact on other part of it, because obviously you cannot get best of all the worlds. But again, evaluation is extremely important. So picking a GC, like if your workload is very heavy on RAM and your servers are always in few hundred GBs, if not terabytes, then you would have to go for a GC that is pause free, which is very efficient in leveraging the hardware. Again, going to the GC documentation might give you that answer. Right? So yeah, these are 7 GC characteristics that are there that would help you pick the next best GC for your next use case. Right? In the coming videos, we'll start going into the different GC algorithms, and we'll start doing deep dive into each one of them, into understanding how they operate, what are the key decisions that those algorithms made to get the performance out of it, like and how do they function. Right? So theory part done. Now we'll start going to the algorithmic part of it. But these 7 key characteristics extremely important for you to know when you are picking your next GC. Hey, what's the scalability? What's the pause time? And most people only think about pause time, but the other 6 are equally important, right? That's exactly where I wanted to create this video for you folks. Nice. Amazing. That's all for this one. Thanks again for watching the video. If you guys like this video, give this video a thumbs up. If you guys like the channel, give this channel a sub, and I'll see you in the next one. Thanks a ton.